Assalamu alaikum and a very good day to all of the participants who are attending this session with me. I am Hassan Rauf from 4G Fertilizer Company in Pakistan, and I'll be discussing our experience of using ETAP RT-based load management system at one of our plant sites, chemical plant sites here in Pakistan. To begin with, a brief about FFC. FFC is the largest producer of urea fertilizer in Pakistan. It was incorporated in 1978 as a joint venture between Fuji Foundation, which is a charitable trust in Pakistan, and Hydro Topsoe of Denmark. It has a production capacity of over 2 million tons per annum. FFC is a member of UNGC, International Fertilizer Association, IFA, and Arab Fertilizer Association as well. So coming to the agenda of today's session, we'll be discussing load management system which are in place at FFC GM, which is one of the two production complexes of urea fertilizer. So this system, which was replaced with ETAP RT-based load management system, was installed at site GM. Then the need of this ELMS upgrade or the load management system, as we call it. What were the limitations of the existing system? What were the options or the key factors which were considered while selecting a suitable upgrade option? And then why finally ETAP RT-based ELMS was chosen? What advantages it brought? And finally the operational flexibility with ILS. What operational flexibility we got with this ETAP RT-based load management system? So to begin with, it is imperative to have an idea of a single line distribution, single line diagram of the power distribution system. So there are two production plants here. One is plant 1 and plant 2 at this site GM. So this is the main substation of plant 1, which is substation 1, and another substation 7, which is the main substation of plant 2. We have two turbo generators of 18 megawatt each, which are hooked up to the system at substation 1 and which are connected through the bus couplers, synchronized through the bus couplers, which remain in closed position. And then we have two emergency generators, each hooked up to its respective substation, one for plant 1 and one for plant 2. So the load management system at FFC GM, there were two systems. One is the electrical load management system, or ELMS, which is the topic of today's session. And this system manages complex load in case of tripping of one turbo generator. It is a PLC-based system. It is common for both plants. That is, it is connected to the loads of both plants. Let me show you in the system topology of the old or existing ELMS. So you can see that there is a redundant communication, redundant control chases in the control room, which are connected through fiber optic links to remote IO racks in substation 1 and substation 7. So this system is connected to the loads of both plant 1 and plant 2. The second system is, we call it the load shedding system. It is a relay-based system, independent for each plant. And it is just to ensure safe shutdown of each plant whenever there is a blackout, that is both turbo generators are tripped. So this phase of project covered only the replacement of this ELMS, electrical load management system. But in the second phase, we also plan to merge this load shedding system of plant 1 with this ELMS, the upgraded ELMS, so as to have a common system for load management at plant 1. So now looking at the need or the need of upgrade or the limitations of the existing ELMS, which forced us to go for this upgrade. So the first and foremost was the obsolescence. We were having an obsolete system. It was a PLC of Allen Bradley, PLC 5x40E. And most of the modules were obsoleted a long time ago, and we were, having real difficulty in getting spares, reliable or new spares for this system. So the reliability of the system was at stake. Same issue was with the software of the system. It was a Windows XP based system, and Windows XP, has been obsoleted again a long time ago. So maintaining the system was quite difficult for us. The second issue was the system incompatibility with the numerical IEDs. So, if you can recall from the topology, that all the interconnections with the system, they were hardwired. There was no communication link with the IEDs. The reason being that this system was not compatible with the numerical IEDs, both from the hardware and software fronts. So you needed a lot of hardware upgrade along with software upgrade in order to interface this system with the numerical IEDs. Then this was the issue on the hardware front. On the software front, we were having the issues of limited system visibility. Um, One of this was that we were having fixed load values for most of the loads. Due to limited real-time monitoring of the loads, most of the load values which were used in the PLC logic, they were fixed. So this assumption was to some extent accurate for the motor loads, which are mostly fixed for the in plant operation, but not for the feeder loads. So this resulted, and again, a conservative approach was being used while having this fixed load value. So this resulted in excessive load shedding in case of any trigger becoming true. Then all system contingencies were not covered. One of this example is the bus tie trip. If you can recall from the SLD that both the generators are interconnected through the bus ties. So if there is a tripping of bus ties, there was no logic configured to cover or take action against such a trigger or such a contingency. Another issue with the software there was no idea of the exact load which will be shed against a trigger in case of a motor start. So to explain this, whenever there is a TG tripping takes place, all the standby loads gets interlocked, except the essential service motors. These are those motors or those motor loads which the start of which must be allowed at any cost. So whenever there is a start signal of any such motor with a TG down, there is a need of additional load shedding because we don't have any reserve at that moment. So we need additional load shedding at that stage. So that was being managed with this motor start trigger. So this is a screenshot from the old system. And if you can see that this is the complete sacrificial load list, which is common for all the essential service motor triggers. So whenever there is an essential service motor starts, depending upon the rating of the motor and the status of the feeders, some of the loads in this list would get tripped. But the operator had no idea at any particular time that, okay, if I am going to start this motor, or if a particular motor comes online, what would be the exact load which will be shed in this scenario. Another limitation in the existing system was that the selection of loads to be shed against TG trip trigger was manual. So again, a screenshot from the old system is shown. So this is all the sacrificial load list. And the system during runtime is calculating based on the feeder status and the system load and the capacity of the generation, what is the requirement of the load shedding. You can see the value in the block required shed. And based on this block required, the operator would then go and manually select each of the load which he want to be shed against this TG trip trigger and to match these two values. And again, because this was operator dependent, it has certain limitations. there was excessive, operator would go with the conservative approach. So he would there was some excessive load shedding each time. And again, there was a potential of misoperation of the system in case a motor loads a load just cuts in, starts or stops, and before the operator makes some selection or changes in this screen, the TG trips. So again, there was a chance of under or overload shedding. So these were the limitations of the existing system. Now moving on to the key factors which we considered while selecting the new system. Obvious was the hardware. The hardware should be industry hardened. It should have a good industrial base. It should be robust. It should be the latest system. But seriously, on the hardware front, it is very difficult to choose a product between different vendors, because all the reliable manufacturers, they are offering very good products, and being an end user, it is really difficult for us to make a selection just based on the hardware. All of the offered systems, they have good industrial base, they have good references. So just based on the hardware, the decision is not that much easier. But with the advent of machine learning and the digital twin based approaches in the software modeling, so the software was the key factor for us, at least to select a suitable upgrade option. And what we considered in the software was the improved visibility. We wanted a system which should improve the visibility of the operations team. They should know on the loads to be tripped in case of a TG trigger. Then the system should be scalable both from the hardware and software fronts. From the hardware, obviously, as we planned this system upgrade in phases, so we wanted this system to be scalable. And on the software front as well, because a modular software system design was more suited to our application, because we can plan the upgrades in phases based on the budget availability. So this was also one of the factors considered by us. Then we wanted a system which would offer and review the existing load management philosophy, including the manual load selection and all the other schemes, and it should offer us some improvements in the load management philosophy. And then the licensing of the system should be perpetual. There should not be any recurring cost for the licensing part. And last, the system should be easily integrable with the IEDs over the latest communication protocol, IC 61850, etc. So these were the key factors which were considered by us for the new system selection. And considering all those factors, and particularly from the software front, the ETAP RT-based load management became the natural choice for us. And what ETAP RT actually, got us on the got it for us, and let's have a brief look on that. So from the hardware front, one of the key issues for us was to have a one window solution for complete system, hardware plus software. So we chose the Schneider Electric hardware, Modicon M580 PLC, and ETAP RT software was used over it. And one of the key advantages for us in that period was that Schneider Electric and ETAP both got merged. Schneider Electric acquired ETAP, and for us this came at a very right time for us, and it was like a one window solution for us, and which made our decision easier in terms of complete system selection. The second advantage which ETAP RT-based system brought us was the digital twin-based or model-driven solution. But this digital twin-based solution again requires a lot of data. So for us, that again would have been an increased time and cost effort to collect all the data from the field, to develop a validated model, or to have a model developed from the scratch or have the model updated. But luckily for us, we had a validated electrical model available with us. We had got complete electrical system studies done only a couple of years before this upgrade. So that was available to us already. So having the idea of this model going live, it was very novel for us. Then this system was model based. So the HMI is just not graphic symbols. There is a model behind each and every symbol, and there is operator has a lot of access to a lot of data, which otherwise is not possible in the existing system. Then system visibility. This was again one of the key factors for us. So ETAP RT literally gave us an unmatched system visibility. So because you have complete model of the electrical system, so using the real-time monitoring and the system analysis tools, you can have great visibility into the system. And due to modular software design, the system was scalable. So we got the basic module with the initial phase of the upgrade. We just got the ETAP load flow module. But since the system is modular and scalable, so we can upgrade it in the future based on our requirements. Real-time load flow analysis was also, again, one of key feature, which gives operators the flexibility to have voltage profiling of the system under different loading conditions, under seasonal variation, under. So this was one of the advantages of ETAP RT-based solution. Event playback can be used. It is actually a two-prong feature. You can use it for after an incident. You can use it to determine the cause, and you can also use it for training purpose. You can simulate certain operational upsets, powers from power system perspective. You can simulate those disturbances, and you can see the effects and train your operation team. So this is also one of the key advantages for us. And the last but not the least was the seamless integration of IEDs. The system was compatible with all the latest communication protocols, including the IC61850. So this was the system architecture. You can see this is the historian servers and the ETAP RT servers along with the workstations. And this is a redundant PLC chassis and connected to the remote IO racks in substation 1 and substation 7. And then we have this IED interfacing with the system at the substation 1 over IC61850 and also another substation with our Modbus TCP. So we actually use two different field fiber optic cable networks, independent networks for data acquisition and the load management purpose. Two different communication networks were used. So coming to the last part of my session, which is the operational flexibility which ILS brought us. So first of all was enhanced visibility through ILS monitor. We were having prior intimation of the loads which will be shed against each trigger. So if I can share the ILS screenshot with you. So on the left side, all the triggers of the system are listed. And on the right side, it is the load list, which will be shed against each trigger. So the loads highlighted are the loads which will be shed against actually a trigger. So this is being dynamically updated. So based on the system conditions, operator can see, okay, this is the load which will be shed if this trigger condition becomes true. So this was the first requirement which was met with this system. Second was the automatic selection and deselection of loads. So there was no operator intervention. System would automatically select and deselect the loads against a trigger. Manual operator intervention was eliminated. Then we have some additional system contingencies which were configured, which was the bus tie trip and the bus loading. Again, this was not available in the old system. Using the real-time data and the analysis and calculations of the ILS, we were able to calculate the megawatt loading on each of the main bus at substation 1. And thus, the operator has increased visibility of the system as well. And another advantage was enabling and disabling of load shedding triggers. This was available to the operator during runtime. He can enable or disable the trigger, as you can see in the screenshot. Selection and deselection of loads during runtime. This was a requirement of FFC that during runtime, operator should be able to select or deselect a load for any of the application, for any of the process conditions. So that advantage, that feature was originally not available, but during implementation phase, ETAP provided us with updated software, and this requirement was also fulfilled. Otherwise, normally the load configuration is done in a separate configuration manager, which is only accessible to engineers. But for only the selection deselection part of load, that was also provided to the operator as well. Then system was flexible enough to accommodate all the existing logics, which is a key requirement in any of the brownfield or retrofit project. Optimization of load to be shed, definitely, with all the automatic load shedding and the real-time monitoring. The load to be shed against a trigger was optimized. And finally, the most critical of any load management system is its speed of operation. So naturally, the ILS on its construction is like this. All the calculations are being done while the system is running. And based on the calculations and the system conditions, the load shedding table is getting uploaded into the PLC. So at the time of a trigger execution, our PLC already has all the information which it needs, and there is no runtime calculation involved. So as a result of this, the speed of operation is quite fast compared to other software solutions. So that is all about the operational flexibility with ILS. I thank you for your time and your attention in attending this session. Thank you and have a nice day. Bye.